So we were here last time. All right. Yeah. Hope you still remember. So let me, quickly go through the story a little bit. Now we are targeting non-homogeneous second-order linear ODE. All right. So this equation, initial value problem, two initial conditions. Our plan at this point, we cannot solve it. Still, a lot of work we need to go through, so we cannot solve it, but we do some preparations. Yeah. All right. The first preparation, we assume we can find a particular solution, y0 of x. That's a particular solution. One very special. How to find it? Another story. Okay? How to find it? Yeah. So it may not be easy, so we delay it. Yeah. Here we just assume we have this particular solution, y0. All right. After that, we consider if we have a general solution, then we use a general solution to subtract that particular solution. And here we use the u. We want to see what new differential equation this u satisfies. Fortunately, this u satisfies the homogeneous version of the previous non-homogeneous differential equation. Homogeneous version, just to drop the right-hand side r function, r of x function. Homogeneous version. So that tells us we should find a general solution of this homogeneous equation. Yeah. If we can find the general solution of the homogeneous, then by adding the y0 particular solution back to that u general solution, we get a y general solution. That's our plan. Okay? All right. Now, our focus is on how to find the general solution of this homogeneous version. Yeah. To find that, here we do some general discussion, high-level abstract general discussion. Yeah. So we want to find two different solutions, y1, y2, for that homogeneous. Yeah. Two different. So why two different? Second order, two, right? So that's pretty natural. First order, one, enough. Second order, we need a two. Third order, we need a three, and so on. Okay? Nth order, we need an n. All right? So that's simple. Yeah. Here, second order. So we want to find two special solutions, but these two special solutions should satisfy certain property. Yeah. Not arbitrary. Arbitrary, we may have problem. So we want these two solutions can represent all other solutions. These two, how special they are representatives. Yeah. So here we use this concept. These two solutions, how special they are representatives for all general solutions for that homogeneous equation. That's the importance. Yeah. They can represent all other solutions. How can they represent all others? Yeah. What's the meaning of that? Let's continue. Yeah. The representative. All right, consider special case. Here, before I explore the special property of y1, y2, first I want to let you think about if y2 equals a constant multiple of y1. K is a constant. So y2 equals a constant multiple of y1, what would happen? Now, then y2 is not a good choice for the representative. Yeah, remember that I use that representative. Not good choice because y1 is good enough to represent y2, right? Think about this. If y2 equals k multiple of y1, how about we just eliminate y2 because we can use y1 to represent y2. We only need to multiply a constant. Simple constant. Okay? We don't need y2. So we can eliminate y2. Yeah. That rationale. All right? So y2 should not be any constant multiple of y1. Then your y1 cannot represent y2, right? Because y2 is a totally different new function. If y2 equals constant multiple of y1, we cannot say y2 is a totally new different function, right? Yeah. Derivative, similar. Integral, similar. How can you say y2 is a totally new, completely new function, right? So, scale up, scale down, not a new, okay? Essentially the same, right? Scale up, scale down, essentially the same. Yeah. So all right, now we want to select y2 should have its own properties, okay? Different derivatives, different integrals, its own properties, y2. Yeah. So y2 is not a constant multiple of, here I say constant multiple of y1. If that k is a function of x, then it's okay, right? K of x times, because derivative would be different, integral would be different, right? So if k is not a constant, then y2 is okay. Because totally different properties, right? Yeah. So, yeah. All right, keeping this in your mind. Yeah. All right. So now, yeah, does not help. Yeah. So I explained this. All right. So we need a solution y2 with this property. Yeah. With this property. Yeah. Not equal to that function for any constant k. Yeah. Yeah. So here we use this special term. That means y1 and y2 must be linearly independent. Yeah. This one we say linearly dependent. y2, yeah, for this case, constant multiple in that case, we call it y2 is linearly dependent to y1. Because constant multiple of y1 is a linear function. y2 is just one special linear function of y1, linearly dependent. Yeah. All right, so the opposite of linear dependence, y2 and y1 must be linearly independent. Yeah. Here, specifically, the meaning is this. Yeah. Later, we will get a criteria to determine how to check if two functions are linearly independent. Yeah, later we will develop a condition, yeah, a special condition. Yeah. All right. So here you use this understanding. Okay, y2 now equal to k multiple of y1 understanding. All right. Yeah. So then, at this point, we introduce the basis concept. Yeah. Now we introduce the basis concept. Yeah. So what's the basis? All right. We say that such y1 and y2 form a basis of the solution of this equation. This y1, y2, very special. All right, so we put them together, okay? It's a set, yeah, one set contains these two functions. So we treat this set of functions a basis of the solution of this homogeneous equation. All right, yeah, So the first time we introduce this basis concept, but we need to continue to spend a lot of time to understand the basis concept. Yeah, because it's a fundamental concept. Yeah. So if you have linear algebra background, that would be much better. Yeah. If not, I will prepare you, because for this function, linear function, accounts for about 1/2 of the materials. 1/2 of material rely on linear algebra. Linear algebra, so important, so critical. And when you go to work, linear algebra also, just second important to calculus. Calculus, which is the first important, all right? Second important, linear algebra. How important it is. Yeah. All right, yeah, the basis. All right, here you treat the two functions inside the basis, two representative functions. How do we use these two special functions to represent arbitrary general solution? Yeah. Next slide. Yeah. You will see. Yeah. How do we represent it? All right. Basis and the linear independence. Let's understand these two concepts. Yeah. All right. Mouse cursor. Yeah, there are two different mouse cursor. Yeah. All right. Yeah. So the same problem. Yeah. Now we want to understand more about the basis, the meaning. Yeah. How important it is. First, a basis should have certain fundamental role in forming a solution of the equation. Yeah, its role, fundamental. Okay? Yeah. Yeah. So there, we use another term for it, so we call it a fundamental system. Yeah. So a basis we call a fundamental system. All right? Yeah. Together we treat it as a system, fundamental system. Yeah. But basis, most of the time people call basis. Yeah. Well known. If you say fundamental system, not many people know it. Yeah. What's the meaning of fundamental system? Right? Not well known. Yeah. Not well known. Yeah. All right. But another thing I like you to pay attention. Here I use this basis, not the basis. Yeah, because we have so many different ways to choose basis. The basis is not unique. Yeah. For a given equation, here we just get its homogeneous version. The basis is not unique. Yeah. There are infinitely many different bases. Here we only need one of the bases. Okay, one of the bases. So many different, but we only need one. One is good enough. Yeah. Yeah. When we choose one, we try to choose as simple as possible. As simple as possible, the basis. Yeah. So it's a basis, not the basis. All right. A basis contains certain number of elements. Yeah. The functions inside this number of elements. That number could be from 1 through infinity. Yeah? Infinitely many functions. Yeah? There is a possibility for some solutions, we need infinitely many functions to represent general solution. Yeah. Yeah. Fortunately for this class, we don't need that. Okay? We only need a finite many. Yeah. For this class. Yeah. All right. For whole math, we may need infinite many. Okay? Yeah. All right. We call that number dimension. Yeah. Dimension. Yeah. This concept, dimension of a basis. Yeah. You count the number of elements inside the basis. All right. For any solution, it is sufficient to use the elements inside the basis to represent it. Okay? Yeah? it's sufficient to use some of the functions. Yeah, not necessarily all. Okay. Yeah. Not necessarily all. 1, 2, 3, up to the dimension number. Okay. Now, we can represent any general solution of the original system. Yeah. Another property. So here I talk about, the common properties for the basis. All right. The way to represent, here it tells you how to represent. The way to represent a solution is a linear combination of the elements in the basis. Here I hope you know the meaning of linear combination. Linear combination, that concept. Yeah, but here I can write one special example for you here. Yeah, all right. Yeah. Here, let me consider a special case. Yeah. We have a basis. Okay? Yeah. So we have a basis with certain number of elements. Yeah. Let's say y1, y2, ... y sub n. Yeah. We have one basis for a homogeneous linear ODE, that system. Yeah. Then linear combination to represent the general solution, as simple as this: y equals C1 constant C1 y1 plus constant C2 y2 plus ... plus constant Cn yn. That's simple. That's what we call the linear combination. Okay? Yeah. This linear combination, yeah, we can treat it this way. Sum of the constant C could be 0. We allow sum of the constant C be 0, but not all 0. All 0, y is trivial solution, right? Yeah, y trivial solution. Here, yeah, we can only consider non-trivial solution. Yeah. Trivial solution. Yeah, trivial solution. Yeah, trivial solution is a special one. Yeah. All right. So here we are only interested in non-trivial solution. Okay. So that means not all C constants are 0. Yeah. At least one C constant not 0. Yeah. So this form, yeah, we can cover all general solution. Yeah. That's the meaning of basis. That's the importance of basis. So we only need to find a basis. That's enough. Then we can represent all general solutions using the, linear combinations of the functions inside the basis. That's simple. Yeah. All right? Yeah. So then another property of this basis. In this problem, order 2, the dimension of the basis is 2. Yeah. 2. Okay? Yeah. Dimension. Yeah. All right. Yeah. So you may ask, why is, yeah. So, but you want to ask why. Okay? Yeah. Why? Yeah. So actually it's simple. Yeah. First, for first order, first we show the basis is 1. Okay. First order. Yeah. That means if you find the second one, we can show it must be a constant multiple of the first one. Yeah. Suppose you find the second one, right? Then you do subtraction, all right? Subtraction, yeah. Yes. Yeah. So first you show first order 1, then you do order reduction. Yeah. Later I will show you order reduction technique. So because we already have 1, then on top of that known one, it's known, it's a known solution, we determine the second one on top of it. So we can do order reduction, reduce the order from 2 to 1. Yeah. So we get another one. Yeah. So you will see by order reduction technique, so we can show we need 2 linearly independent basis functions. Yeah. All right. So dimension 2. The 2 elements of the basis must be linearly independent. Yeah. Here I pretty much give you all the basic properties of the basis concept. Yeah. Yeah. So if you understand all the properties listed here, so you understand basis quite well. Okay? Yeah. Later you need to build up your experience to understand the basis. Yeah. All right. Yeah. How to understand linear independence? Yeah. All right. Assume that y1, y2, 2 functions are linearly independent. Yeah. So that means there does not exist k1, k2, 2 constant. Yeah. K1, K2, here. We assume they are constant. All right. Such that the linear combination, yeah, look at this. This is a linear combination of y1, y2, right? Yeah. K1 times y1 plus K2 times y2. So their linear combination equals 0 function. Here, equals 0 means equals 0 function. As a function, equals 0. Okay? So on certain interval I, yeah, on certain interval I, yeah, because in the real world application problem, we may consider our solutions, functions on certain interval. Yeah, yeah, not necessarily the whole real line. Yeah, part of a real line interval I. Okay, yeah, sometimes the whole real line. Yeah, but most of the time only on an interval of the real line. Okay, yeah, real world applications. There is a range, yeah, range for the variable to be considered, right? A variable in the range. Yeah. Okay, all right. In a domain, yeah. So the formal name we call domain. Yeah, yeah. Range, that's the y value we call range, right? Yeah, y value has some range. And x value we call the domain of the variable. Yeah. It's some interval. Yeah. All right, next. (8.3) Find a basis by reduction of order. Now I show you how to do the reduction of order. Just some special substitution. Yeah, some special substitution. We can do the reduction. Yeah. All right. Yeah. Reduction of order approach. Yeah. Find the basis of solution of this special example. Yeah. In this example, first we guess a simple solution. Yeah. Because we need to have the first solution, non-trivial solution. In order to apply this technique, we need to have the first solution. Yeah. Yeah. So this one, yeah, it is given in the first solution, yeah, y1 equals x. X, yeah, it's a simple solution. Yeah. So you can check this is a solution. Because y double prime, if you plug in y double prime 0, so the first term is gone, 0, okay? Second term, y prime equals 1, 1 times negative x, then positive x here cancel out, you get a 0, okay? So it is a solution. Now, we want to find the second solution. Second solution in the basis, so linearly independent. Yeah. How do we find that one? Yeah. here. All right. Yeah. Yeah. How to find the second solution? Yeah. There is a, substitution, special substitution method. Yeah. We just use the same method. Later, when we have the similar problem, we use the same method. Yeah. The method is do this substitution. Your y equals some unknown function u. U is a function. Here, do not treat u as constant. Okay, unknown function u times y1. Here, u times x. This substitution works well. All right, it works well. Yeah. So let's plug in. Simplify it and see what is the new different ODE for u function. Yeah. New. So we take y prime by the product rule. We have the derivative like this, product rule of derivative. We take double prime. After simplification, we have this representation. Yeah. Now, let's plug in back to the original equation. Yeah. It's this one. Yeah. We need to do simplification. Okay, cancel out certain terms, combine the like terms, and at the end, this is one-step simplification. Yeah, not the final. Yeah, one step. All right. But ux is cancel out. You can see ux term cancel out. Why? Because minus x times u. So ux is cancel out. It's gone. Okay. All right. So we have a simpler one. We do further simplification. So we get this one, this new equation. Yeah. This new equation, you see second order homogeneous linear ODE. Yeah. But one thing, u term is gone. U term is gone. Simpler than original one. Original one, the y term is there. Here, u term is gone. That good property, we can take advantage of it. Yeah? Just take advantage of it. Yeah. How to take advantage of it? Because we can assume u prime is a new function. U double prime, just the prime of this new function, it becomes the first order differential equation, right? Think about that. Because we can treat u prime as a new function, v. How about that? V function. V equals u prime. Then this equation just the first order differential equation for v function. Much simpler. Because we know how to solve first order. Yeah? Here we convert it to first order. That's what we call the title, reduction of order. Because order we reduce from 2 to 1 after we introduce that v function. V. All right. Here, let the v equals u prime. So we modify the last equation to this time you get a first order differential equation. We can solve it. This one, we can solve it. First order differential, right? First, a separable, right? Yeah. Can you see that it's a separable ODE? Yeah, the simplest. We just use separable. Okay, all right. So let's write a separable way. Left-hand side, dv over v. Yeah. All v terms we put at the left-hand side. All x terms we put at the right-hand side. Can we use integration to find the solution? Yeah. Do integral, right? Yeah. Left-hand side, natural log of absolute value of v. But the question, do you know how to do the integral at the right-hand side? It's a fraction. Do you have any idea? Just recall. Yeah. What do you learn in calculus? In calculus, when you see the integral of that fraction, is there any special technique you can apply to find it? A special name? Anyone remember a special name? Great, partial, correct. Partial fraction. That's the name of the technique. Okay, all right. So let's recall that little technique, the partial fraction technique. All right. So what's the partial fraction? We need to decompose this fraction in as the sum of two simpler fractions. Yeah. Here, because denominator is a quadratic function, degree 2 polynomial, quadratic. Now we can decompose, right? Yeah, we can decompose. It has two factors, right? Or two linear factors. Let's call precisely, yeah, because here if I write, you know, denominator x squared minus x, yeah, it's a little slow, yeah, x times x minus 1. Okay, yeah. So here, two linear factors. Yeah. Now, with these two linear factors, you decompose. So each linear factor, you use it as the denominator to form a simpler fraction. But the numerator is a constant a to be determined. Here, the numerator constant b to be determined. The next question, do you know how to determine a and b? How to determine a and b? Two constant. Yeah. This is identity. Yeah, this is identity. But the question, how to determine a and b?
You have to multiply a or b by
Yeah.
so you can cancel.
Yeah, right. Yeah. Multiply common denominator. Yeah. Remove the denominator. Common denominator. All right. Yeah. So here the idea. So, yeah. Because my pen, you know, lagging. Yeah. I notice significant lagging. Yeah. All right. So here, the basic method: multiply the common denominator both sides, so you get some equation, right? Some equation. You compare the corresponding coefficient. Yeah. Coefficient of x, coefficient of constant must be equal. Coefficient of x, both sides must be equal. So you have first equation. Coefficient of constant, both sides must be equal. Second equation. You have two unknowns, a, b, two equations. You can solve for a and b. Yeah. That's the basic method. Okay? Yeah. All right. So here I just write the solution. Answer. I just write answer. Answer is this. Partial fraction decomposition, like that. Okay. Then to take integral, we have the formula. Yeah. So the integral, we can use natural log, absolute value to write it. Yeah. Okay. Yeah. All right. Yeah. And simplification like that. Yeah. Absolute value, we want to remove absolute value, right? Yeah, not convenient. Yeah. To remove, then we need to consider. Yeah. So here, one way to remove, we take square both sides. It's gone, right? Yeah. One way to consider to remove the absolute value sign. Yeah. Taking square. Yeah. So from the square, we have plus minus, right? Yeah. If we take square root, we have plus minus. You know, two versions, two of these. Yeah. But here, we only need to find one special v, right? Yeah. Because when we find 1, 2, y2 is a special solution, right? Special solution, we can choose simpler version. Yeah. Plus minus, yeah, plus simpler, so we choose the plus version. Yeah. Okay. All right. Yeah. So after v, you can get a u. After u, you can get a, second y. Yeah. Here, I leave the remaining work to you. Okay. Yeah. Remaining work. Yeah. To you. Okay. Yeah. Yeah. So from this example, so you can see, yeah, how to apply that reduction by order technique. Yeah. Partial fraction, some of you, yeah, so after today's class, you may go back to, look at your calculus book, yeah, or search the web, yeah, how to do the, partial fraction technique. Yeah, yeah. Partial fraction technique, okay? Yeah, all right. Next, general process, reduction of order. Yeah. Because the previous one, that's just special example. Here, let's move that idea to the general case. Yeah. All right. General case, the first step, we need to find the first solution, y1. Yeah. How to find another question? Yeah. Sometimes you can guess, sometimes you need to apply some special method. Yeah. 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 So let's look at that later. Yeah. y1. Yeah. All right. After that, step 2, find second solution with this special substitution. Yeah. All right. So then you just take first derivative, second derivative, then you go back to the original equation and do some simplification. Yeah. Why you do simplification? So here, that's the result after simplification. Yeah. But you can see the last parenthesis, inside the parenthesis, that's just when you plug in y1 into the original equation, that should be 0. Because we assume y1 is the first solution. So you can see, if y1 is the first solution, then the last term is gone. The last term is gone. Okay? Yeah. All right. After that, you make another substitution. V equals u prime. So you can write a first order ODE with respect to the u function. And you can find a solution. Yeah. Yeah. So here, you do the separable version, integral, to find the v function. Okay? Yeah. So v, yeah. That's 1, and you get a simplification like this. Yeah. Then we want to write a v expression. Yeah. Yeah. So the v we can write this way. Yeah. Another step. Yeah. V. This time we remove the absolute value sign. Yeah. Because we only want a special solution, one special solution. Okay? Yeah. So when we remove, we know we only want to get a one special solution, not a general. For the general solution, then you should be careful. Okay? Yeah. Because general solution, you want to cover all possibilities. Special solution, we don't need to cover all possibilities, right? We just want to take one possibility. That's enough. Okay? Look at the goal. Our goal is find one special solution. So you only take one possibility. All right? If your goal is find all solutions, you need to cover all possibilities. Okay? Yeah. Go back to the goal. Yeah. When you determine how to handle the absolute value sign, think about what's the objective here. Okay? Yeah. If just find a special solution, then you have a lot of freedom to get the simplest expression. If the objectives we need to represent all the general solutions, then you should be careful. Okay? You need to cover all possibilities. So do not miss anyone. Okay? Use constant. Use different ways, cases to cover all possibilities. Yeah. If your objective is the whole solution. All solutions. All right? Yeah. Then after v, we can get a u because it's integral of v by the definition, right? Yeah, v equals u prime. So if we have v, we go back to u, we just take one integral. That's simple, okay? All right. Then the last step, we can write y2 formula, yeah, y1 times integral of v dx. Yeah, that's the general formula. Yeah, with these formulas, then given some second order linear homogeneous equation, yeah, so we just apply these two formulas. Okay, yeah. So we go through, all these things. Yeah. There. In your calculation, you can skip all these things. All right, you don't need to repeat. Yeah, that's our derivation process. Okay, yeah, we can skip. Yeah, yeah. So we jump to these two formulas immediately. Okay. Yeah. But you know how to derive, yeah, because we should understand how to derive these formulas. Yeah. Especially, we need to know the techniques. These two substitutions. Yeah. Because sometimes we need to apply these techniques ourselves. Yeah. All right. Any question? Yeah. Yeah. All right. Yeah. So we finish this topic. Yeah. Next. Example. Find the basis by reduction of order. So let's do calculation. Yeah. Do one example. Here we just apply the formulas, yeah. But you need to be familiar with integrals. Yeah. Yeah. Let's look at example here. Find the basis for ODE, this equation. Yeah. Yeah. All right. But the first one is given. Yes, the first one, because if you want to guess the first one, it's hard. Yeah. It's hard for me. Yeah. Yeah. We need a lot of experience, a lot of testing, a lot of work. We can get the first one. Yeah. All right. But here it is given, first one, then by our reduction by order technique, we can find y2. Yeah. Yeah. So let's do it again. Yeah, this time. Yeah. All right. Solution. Yeah. Here, let me write the formula here. Okay. Because, we need to get a formula ready. These two formulas ready. Yeah. Yeah. All right. Yeah. P. Yeah. First, let's do the standard form, because the original equation is not in the standard form. First, let's convert it to the standard form. Yeah. With the leading coefficient of y double prime, that leading coefficient equals 1. That's the standard form. Then we have the p function. Okay. Yeah. Otherwise, your p function would be wrong. All right. So if you do not do the standard form, your p function would be wrong. Yeah. So this time p function 2 over x, that's our p function. So we can calculate our v function, y1 given, so we can write y1 reciprocal 1 over y1 squared. So we take a reciprocal. Yeah. Then exp function integral of the simple function. Yeah. So yeah. Then exponential function, its exponent -2 times ln of absolute value of x. Yeah. Then, at this point, we have the experience. Yeah. We have the experience because when you see exponential, natural log, these two functions, we can do cancellation, right? Exponential e function and a natural log, there is some kind of cancellation. Yeah. Here, let me recall. Remember last time I wrote that formula. Yeah. So e to the ln of x equals x. We use this formula, simplification formula. Okay? All right. To apply this formula, this minus 2, we need to bring it, inside natural log. Yeah? Minus 2, quite annoying, right? Because if we have, something, something before the natural log function, we cannot apply this formula. All right? Yeah. So for that reason, we write another step to, this time -2, negative, we know it's reciprocal, 1 over, right? 2, that's square. All right? Square, absolute value is gone. Yeah? So that's very friendly. Yeah? Absolute value is gone. Okay? 1 over x squared. Yeah? Now cancellation. EXP and the ln can be canceled out, right? You remember that formula? EXP, just the e function, natural log, cancellation. Whatever inside, we keep it. Whatever inside, we just keep it. Okay? Inside 1 over x squared, we keep it. Right? After the cancellation, 1 over x squared, another cancellation, right? X squared cancellation. Okay? So we get a 1 over cosine square. Okay? Yeah. That is secant square of x. So our v function, after we simplify it, at the end, it is a secant square function, v. Okay? So that's the first formula. Second formula, yeah. Y2 formula. Y2, yeah. Now this time, yeah. Everything is known. Y1, we copy Y1 inside integral of secant square of x dx. Do you know, any of you know the formula? What is the integral of secant square? Good, good. Perfect, perfect. Yeah, yeah. Tangent, tangent. Okay, yeah. Great. Yeah. All right. Cosine of x over x times tangent. Okay? Tangent, sine over cosine, cosine cancel out. So the answer is sine of x over x. So Y2 function is found. Is found. Yeah. Then we have the basis, right? Y1, Y2, we put together, we get a basis of this homogeneous system. And we can represent the general solution of, so here, conclusion, the general solution, linear combination of Y1, Y2, linear combination C1 times Y1 plus C2 times Y2. That's the general solution of the homogeneous equation. Okay? Yeah. Then, because after we have the general solution, if we are given initial condition, we need 2 initial conditions, right? Yeah. Y of x0, y prime of x0, if we are given 2 initial conditions, we can find the C1, C2 values, right? Yeah. So we can solve IVP problem. Yeah. After the formula of the general solution, then you can solve the initial value problem. Yeah. Yeah. All right. Yeah. So that's this example. Yeah. All right. Then here, yeah, I leave one question. Yeah. Why? So we put these two functions together. Why it is a basis? Okay. Why it is a basis? Yeah. Yeah. Later, I just mentioned there is a criterion. Yeah. There is some formula you apply to check some condition, tell you it's a basis or not. Yeah. 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 We will get there. Yeah. Yeah. All right. Yeah. So let's delay. Yeah. This question we will answer later. All right. 8.4. Homogeneous second order linear ODEs with constant coefficients. Yeah. This time, yeah. Constant. We know that's the simplest possible ODE, second order linear ODE. Simplest. So we should solve the simplest case first, right? Yeah. So this topic, we want to find all the possible solutions for this simplest case. Yeah. All right.